Okay, Martin, thank you very much for the introduction. I would also like to welcome all of you to my webinar today called Coupled 3D Field and Circuit Simulation. So what I would like to show you during the next 45 minutes is how to set up such a coupled simulation and what advantages you can expect from using this coupling. Because of course we do this coupling because we expect to have advantages over each of the simulations standalone, and that's what I would like to show you. But first we have to understand some of the basics, and how I would like to start with is a pretty simple model. So we have a microstrip with a driver, a series component, and a termination resistance. It's about 10 centimeter long, 2 centimeter in the width, and 180 micrometer of thickness for the FR4 material. So very, let's say, very typical setup that we see here. And what I would like to do is that I would like to drive this signal, this trace here. I would like to drive it with a signal, which you can see here. It's basically a 200 nanohertz, 200 megahertz signal, because we have 5 nanoseconds of time and we have a rise time of 250 picoseconds. So pretty fast rise time, and this is the signal that I would like to drive the setup with. So I start the simulation straight away. What I'm doing is I'm driving directly in time domain, driving the setup here with the signal that I have showed you. So because the series resistance is basically a short, and I have a pretty high termination resistance, I expect that my signal will look basically pretty bad. And while the time domain simulation is running, so I'm using the full wave 3D transient solver based on the FIT technique here, I can already basically go into the result tree, and I can take a look at the results that are recorded through the simulation. So even though it's finished, what I did, I chosen to have a simulation time of 10 nanoseconds, which are 2 periods, and I can go now and look into the folder which is called lumped element, which gives me the voltages, signals, voltages in time domain, and the lumped elements. So of course at the series I do not expect to have any voltage, while at the termination, at the far end side of the signal trace, get a pretty big ringing, of course, because the line is completely unmatched and I have a pretty fast signal. So let me copy this result, and now I create a new folder where I will compare the results, and I copy my folder into it. So I said this is the value at the termination, it's the voltage at the termination when I have used the 0.001 ohm. If now I would like to see what is the effect when changing the sum of these elements, for example changing the series resistance, I can go here and the definition of the lumped element, and I change it now to be a better match, like of 50 ohm. But when I do this, of course the software will ask me that it wants to delete results. When modeling lumped elements, as I did in this case, the lumped elements are placed into the 3D model. So any change to the value of the lumped element will force me to rerun the full 3D simulation. That's what I do now. I restart it. It says the transient analysis is processing the excitation. It's again the 10 nanosecond excitation that I'm feeding into the model. And you can see that that might become time consuming. Of course, this is a very simple model, but for a complex model where the 3D simulations might be more complex or more time consuming, changing these values and rerunning everything just because I want to change the value of a resistor, that seems not acceptable. And this is something which we can solve much better with a coupled simulation. But let's first take a look at the results of the simulation. So after changing the series resistor into 50 ohm, I can go back into the tree, look at the termination. Of course, now my signals look somehow better. Still not perfect, but I can place them in my comparison folder. I just name it to be the 50 ohm result, and that's how it goes. So every time you want to change the value here of the lumped element, you need to rerun the full 3D simulation, and that's of course something we can do better by defining a coupled simulation. So the first and most important thing for coupled simulation is that each port, every port, serves like an interface for us between the 3D and the circuit simulation. So what I did now, instead of defining lumped element values, I have defined ports at all the positions where I need them, basically the driver, the series, and the termination resistor. And now I need to start the simulation. And what the simulation is now doing, it's running a broadband analysis of the geometry. So I am no longer using directly this rectangular signal. The signal that is used by the tool is chosen automatically depending on what excitation frequency I have defined. So I run this from 0 to 4 gigahertz, so it chooses one particular Gaussian pulse, and with this Gaussian pulse it's run a broadband analysis obtaining the S parameters, and the S parameters describe basically the coupling between the three ports that I have defined. You can see this is still running on the fly, and it's calculating one port after the other. So now we arrive at the third port, and once this is finished we can see how the S parameters look like. But as before, we are maybe not even interested in the S parameters, we are interested in voltages and currents. But in order to obtain them, I switch now to the schematic. So you can see this is the 3D plot or the 3D model, and I click onto the schematic. And then I'm getting a schematic where the three different ports are here. They are connected at this block. So this block represents my 3D model, and I have three ports to which I can connect certain circuit elements. We support typically all popular or standard circuit elements. In this case, of course, it's pretty simple because we run the simulation here just with resistors and with a driver. So now I need to define a new task, which will be a circuit task, and the circuit task will be a transient simulation, a transient circuit, where I define a signal at port 1, and I've chosen to be the same values like I used before, and I've chosen it to be a voltage signal that will drive port 1. Here's the simulation time of 10 nanoseconds, here is the signal setup, and this is the series resistor and the termination resistors. They I have defined in the same way what I did before in the model with the lumped elements. And also I have placed probes in order to see the voltages and the currents. And if I now run, you can see that it's lightning fast. It's really quick, because of course it's now a standalone circuit simulation. And if I go here, I can visualize the voltages, and I can get the voltages here at the termination, and I can copy and paste them into the folder that I used previously. And you can see that this coupled simulation delivered basically the same result. That's the simulation where we have placed all the lumped components into it. So I can call this termination 50 ohm circuit. And now I can go back to the other model, back to the circuit schematic, and change the series resistor from previously 50 ohm now back to 1 ohm, or make it maybe a milliohm or 0.001, and rerun the transient task. I said, okay, update. And again, it's lightning fast. So the 3D model didn't change. I did not need any resimulation of the 3D model. I have just resimulated the circuit. And if I look at the voltages at the termination and copy and paste them back into the folder where I compare, you can also see some excellent agreement of the coupled model to the model where the lumped elements were placed directly into the 3D schematic. So you can see the versatility and the speed gain you are getting if you are considering to set up such a coupled simulation. So let me go back to the PowerPoint we had before. So this is our model, and let me summarize what we have seen in the online demonstration. So if you put your lumped elements directly into the 3D model, you need to resimulate the complete 3D model when any of the component values has changed. This is okay if you want to keep these elements anyway fixed and you do not want to touch them. But if you consider to change the values of your lumped elements, then you should use the co-simulation. And in the co-simulation, instead of placing the lumped element directly into the 3D model, you place a port there. Each of the ports will give you a pin in the Design Studio schematic, and on the schematic This is where you connect your excitation, you connect your drivers, you connect any RLC models, and this is also where you define the signal which you want to use to excite the structure. There is of course a little bit of overhead because now the 3D simulation needs to simulate for 3 different ports. But again, if you want to change these values, this overhead is mostly not critical, and the coupled simulation will be much faster than putting everything directly into the 3D model. So this is the demonstration that I gave you. And now let's take a look at the schematic that I have shown you, because for a typical SPICE engineer, this schematic looks a little bit odd. So what I have said, what I have described already, that this block here at the bottom, this block contains the information about the 3D model, and I'm getting the 3 different pins that are corresponding to the ports of the 3D schematic. And now you can see that each component they have connected has a certain ground symbol. And this is something which typically at this point is confusing SPICE engineers, but we need to understand what is the meaning of ground. If we look at a circuit ground, so a circuit ground is a reference because it tells the voltage there is 0, and on a circuit ground a current can flow out and in basically instantaneously. It's an ideal connection which allows the current loop to close. And people seeing this type of schematic often start to thinking, okay, the termination resistance has been connected to the ground, so this is okay, but why do I put a ground here even if this is a series resistor? And the answer is that these grounds on the circuit are local grounds. So they are used purely by the circuit schematic because in reality there is no ground. So a real structure does not have the property of ground. Ground is a concept that is used on the circuit, but it does not happen in reality. What happens in reality is that you have some certain conductor. In the case here, it's a very simple metallic plane, a certain conductor on which the return current will flow. But the certain conductor, of course, has physical properties. It got finite propagation time. It's not ideally instantaneous. Actually, it's on a circuit. So it got finite propagation time. It got properties like inductance. It got properties like resistance. And that already at this point should make it clear that these ground symbols that we see on the circuit, they have no connection to any physical shape that we see. So there is a different explanation where we have them, and I will give them to you on the following slides. But one more thing about the voltage 0. Sometimes people ask me, how do I put a voltage of 0 into the 3D model? This is a high frequency simulation. It's simply not possible to have a voltage of 0 because at higher frequencies, when the wavelength is becoming corresponding to the size of your structure, a metallic surface is not equipotential. This does not happen. If we look at the electric fields at 2 gigahertz of the signal trace that I have simulated, you can clearly see there is a wavelength effect. So this is the electric field between the signal trace and the reference layer. And you cannot say that there is some potential of 0 to which you can refer. So the only thing what you can do, a voltage, when you want to see a voltage is always something which is measured between 2 points. And you need to make sure that these points are very close to each other, otherwise the voltage at higher frequencies is no longer independent from the path. So that makes the voltage a little bit tricky to use, and therefore I also tend to do most of my explanation that I will show you on the following slides in terms of the current, because it's much easier to understand. So let's go back to the schematic that I've shown you before. And now, as I have already said several times, the 3D model passes a set of S parameters to the circuit. And S parameters, in order to connect any other schematic to the S parameters, you are using ideal transformers. So basically what is done in the interior of the block, as you can see, we have our set of S parameters which are provided from the circuit simulation, and then we connect all the components by using ideal transformators. This is not done by intention. This is the way you use S parameters on a circuit schematic. So this is basically microwave theory from the 1960s. So this is not invented by CST. It's the way how you do it. And if you, for example, want to use measured S parameters that you have measured with your VNA and you want to use them on the schematic, they will be treated in exactly the same way as we do it here. So because they are connected by an ideal transformer, basically, each of the sub-circuit is floating against each others. So therefore, each of the sub-circuits actually needs a certain reference. And by putting in this way, by grounding the one side of the transformer arm internally, so you don't basically here you don't see this internal grounds. But by grounding this internally and then defining a grounding symbol on the schematic, on the actual schematic where we connect our elements, we make sure that the current loop for each of the sub-circuit is closed again. And this is the way you have to think of. You have to think that here the ground symbol is just used to close the current loop. Again, it does not have to do anything with the 3D structure. It is used to close the current loop. And this is the slide which basically is the most important for you if you do not want to dig into the details of the simulation. It tells you basically how the connection is happening. And it's very, very simple. You can say that everything that has been placed in between the 3D model that we see here, the 3D block, and the ground element, everything that has been placed there will be placed at the position of the red cone in the 3D model. So this red cone is the position of the port, and what are placed in between here and the ground symbol, this is what has been placed into this cone. This is how the connecting of the element happens. And in many, many cases, I would recommend to really use one port for each connecting element, because then the setup is always pretty clear. And again, these ground symbols here that you can see, they are used to close the current loop. They are not connected to any of the structure. And we can take a look how that happens if we go into another model. So I go here into a model first here, where we see the same, basically the similar setup as before. Now I have a driver port here and a series port here, and what I'm looking now are time domain results. So I'm looking at the time domain surface currents here. I activate them, and I have driven the structure with a small pulse, and now I can go through time. So we are currently at the time of 0, and I can make the pulse basically move here on the signal trace. So what we see is the current on the signal trace and also on the return on the reference layer. So move it up a little bit, maybe create a few more arrows just to visualize, and you can see this is basically a signal, rectangular signal that is running on the structure. And now we are at the time of 80 picoseconds. We can move on. The signal propagates, and once it arrives at the position of port 2, at the position of the red cone, this is where the coupling to the circuit is happening, I can switch over. So you can see we are now at 0.16 nanoseconds. I can switch over to the schematic, and I can look at the results. So if I look at the voltages at the excuse me, not voltages, I look at the currents at the series size. So I can zoom in here a little bit, and I can place an axis marker of 0.16. So you can see this is exactly the rising flank where the current flows through the schematic. And that means the current flows through this series resistor, and because we have closed the loop, it can flow through this resistor and continue flowing basically along the signal trace on the other side. So this is a simple picture on how to understand the coupling. So you can see the current arrives it's handed over to the circuit schematic, it flows through the circuit schematic and continues to flowing on the right hand side simply because the port has been placed like this. So passing over the current to the schematic means that the current will again leave the schematic basically when it flow through the when the current loop on the schematic has been closed. Then the current can exit the port again and continue flowing into the 3D model. So I know that it's a very simple way to describe, but I think it's a pretty visual way to describe things. And maybe you have noticed that what I showed you in the previous example was a little bit different, because I was showing you time domain results, where we could really see the time domain propagation of a pulse into the 3D model. So when we talk about the co-simulation or the coupled simulations, there are two approaches. In the first approach, I used what I call the traditional co-simulation. In the traditional co-simulation, the structure is analyzed using 3D solver. Then the 3D solver provides the full S matrix to the schematic, and then the schematic is basically running independent from the 3D solver, but still will have access to the fields only in frequency domain with something which we call combined results. This is something I will show you in a few minutes. But what I have used to visualize the time domain currents is what is the so-called true transient simulation. The true transient simulation is pretty special. It's a very unique feature that we have on, I think, so far as I know, only CST can offer it, and it works only together with a transient solver. What is happening in the true transient simulation is that basically you do the time stepping at the circuit and the 3D level simultaneously. So it's like putting all the elements that are defined on the circuit, they are put really into the 3D model. So in case of resistors, it's of course a little bit boring putting resistors in the 3D model. We have shown that we can do this by logged elements. But if you would, for example, use SPICE models, we might like embed the SPICE models into the time domain 3D model, and this is pretty special. This you could use, for example, to visualize switching behavior, not only in frequency domain, but real time domain switching on a circuit. This is what we call true transient simulation. Of course, as I'm telling you, because you are putting the elements right away into the 3D model, it needs to rerun the full 3D model if any component has changed. So this is the true transient simulation. It's pretty powerful for certain application classes, but we will first continue with the traditional co-simulation. Traditional means first the structure is analyzed by the 3D solver in a broadband fashion, then we move on to the schematic, we run the schematic task, and we then are able to obtain also results on the field results using the combined results approach, which I would like to introduce to you. But first, let me go back one more time and show you a setup where people typically, again, SPICE engineers are often a little bit confused with this setup, and that's why I have added a slide to explain this. So imagine we have something like this. We have two ports and we connect them to the same ground. Does this make a difference? Is it different from the setup we had before, where there were ground symbols on the schematic? And it's funny because people tend to interpret it in this way or this way, but there is only one clear answer. It's, of course, it does not make any difference, because if some node is connected to the ground, it's automatically, of course, connected to all other grounds. So connecting it to one ground symbol or two ground symbols doesn't make any difference. But what is happening here, or how you might, the best way to understand what we did is, again, thinking about the current. If you think about how the current will flow through this particular resistor to the ground and then close the ground loop. But it will close the ground loop inside its own port. It will never flow from one to the other port, because there is no reason for it. So the ground loop is always closed for each of the subcircuits. So this is not an issue, and you can define this. Even if when I set up my models, I personally tend to give each component its own ground symbol, but it is not necessarily needed. You can connect them all to the same ground. It will make no difference. What might of course happen, or what will make a difference, is of course if you disconnect the ground. What we did now is that we have internally connected on the schematic two different ports. And this might be dangerous, because let me show you an example what can happen. If we connect two different ports on the schematic which are separated from each other, what will happen? So let's go to the schematic. I have again the same driver. I have a termination which doesn't matter too much, but I have connected the series port by a 1 ohm resistor to the loop. So I have connected this and this position. So what will happen? Let's go to the surface current monitor and again visualize the current in time domain. So I create again the current pulse the same way I did before. And now on the schematic, this port and this port is connected. So what will happen with the current? The current will flow on the signal trace, and of course it will disappear here. I mean, of course, some of the current will continue flowing, but some of the current will magically jump from port 2 to port 4 and continue flowing on this loop. So that is of course in the model that we see here, in the 3D model that we have created, it's completely unphysical. The current simply disappeared and appeared on a different position. So that means if you're connecting two ports to each other on the schematic, you have to be careful of what you are doing. Of course, there are cases where you, for example, would do is, for example, if you want to model a transformer onto the schematic, you need to connect these two ports to each other because you want the current to jump from one point to the other. But if you connect ports that are spatially very much separated from each other, setting up this coupled simulation will give you nonsense results. So you have to be careful of what you are doing. So coming back to this two-port setup, so here's something, or here's a guideline when it is acceptable. As long as the distance of these two ports is very much smaller than the wavelengths of interest, then it's okay to connect them. Then you might do this, like you can see here. Instead of putting a port in series here, I put two ports to the reference layer, and then basically the current arrives here, it disappears here and appears again here, and this is okay. This doesn't change too much of the physics because we have only a tiny violation. However, as you think about the loop before, there the violation was really huge. Another, let's say, special case might be if you have really measured data which contains some delay, and instead of putting the resistor there, you have maybe a touchstone file with it's including some delay because it has been de-embedded in a way that really you have measured to certain lengths. Then putting this port separated from each other might even be the right choice. But these are special cases that I will not discuss today because today is just an introductory course. So what you have seen up to now is how to connect simple elements. But now, of course, the question would be, what do I do if I have something more complex? And something more complex might be, for example, a transformer that I would like to connect. A transformer is a 3-pin device, so I need to connect 3 pins to each. And how do I do it the best way, or the simplest way, is by using something which I call a virtual reference. So what you see here is basically, okay, we said this is a DC in, here we put a load, and here's the gate driver of a transistor. And at this position, we have a transistor. And I have placed 3 ports, and these 3 ports connect to a metal plate. So don't be confused by this shining through. This is just a graphical problem. You can see these 3 ports are just connected to the metallic plate that is on top. And because I have 3 ports on this side, I will get also 3 ports on the schematic. Why do I need to do this? Of course, in the schematic itself, it will be not important. This virtual reference is not needed, but this virtual reference is needed for the 3D solver. So when the 3D solver runs the analysis of the structure, it needs to close the current loops. And by adding this virtual reference, I have like a possibility for the 3D solver to close the current loop. It's helping the solver to find the proper S parameters, and then I go onto the schematic like you can see here. So like I said, port 1 is driving a 12 volt into it, port 2 is a load, the 3D ports 1 and 2, while at port 3, which is here at the bottom, I put a driver to drive the gate of a N MOSFET transistor that I have placed here. So here's the drain, gate, and source. These are the 3 pins that are connected properly to the 3D model. And then I can go again to the schematic and define a transient task. So I define some switching, which is far slower than the switching I used before, because I need to make sure that the transistor can respond to the switching. So I'm simulating now for 20 microseconds with a total time of with two pulses again. Let me just run the simulation again. This will be very, very fast. The circuit is quickly calculated. We can take a look again at the currents first. So I can see the currents. Okay, this is the input current and this is the load current. So basically I'm switching the current on and off by making the transistor, by basically switching the transistor on and off. And the current that goes through the drain and through the source is just inverse, because I have defined the probe to be inverse, and I can see there is no current at the gate. So everything is pretty fine and pretty as I would expect it. But now if I go to the voltages, things look a little bit strange. For example, if I look at the voltage at the gate, even if I'm switching it at port 1, I'm switching the voltage with a 5 volt signal. The voltage at the gate looks pretty strange. It's at -4 and it's switching up to something like 1. And what is the problem in this case, or why is it bad what we see? Because what we see, the gate, I have defined a probe being here at the gate. So that is the local voltage between my virtual reference and basically the voltage between the virtual reference and the microstrip that is connecting to this virtual reference. So what I'm getting directly is the voltage between these 2 points. And that does not mean anything to the transistor. In order to switch the transistor, I need to see the voltage between the gate and the source. So that means I need to define a different probe. So I go here, just remove these probes, and what I need to do at this point, I need to define basically a differential probe. I need to define a probe which measures the voltage between these 2 points, not between the virtual reference, but between the gate and the source itself. That I can do. I can define a differential probe in between gate and source and rerun my simulation. And then again, the currents are unchanged. Okay, the one probe is disappeared. That's why I don't see any inverse current. But the voltages now, so I have defined it to be P1. Now you can see that the voltages, as I have expected, they show me the switching, or the 5 volt that I used to switch the transistor. So it's also something that you need to, when using such a virtual reference, sometimes the values, the local values, have not much meaning for you. Then you have to really understand which voltage, which current are you really looking for. So this is how you would set up a co-simulation for a more complex setup. And it also brings us to something which is the simulation speed actually. So you could see that the broadband analysis, what we see on the right hand side, took just 20 nanoseconds for each of the ports. So it's 6 times 20 nanoseconds. However, I wanted the switching that I did on the transistor was much slower. I was switching just to 20 microseconds. And often, for example, in power electronics applications, we need to switch for a pretty long time. We need to switch even for milliseconds. And then you would never use the true transient simulation, because that would be far too slow. What you do there is really you use this coupled simulation also in order to being able to simulate pretty long switching times. And because we do this, we can no longer visualize the fields and the currents by the true transient approach. We need to find a different way to visualize the currents, and this is by using the so-called combined results. So combined results is something which is based on the superposition principle. And we start first with an example in the frequency domain. What combined results is doing it allows you to visualize the fields and currents with the attached circuit, but as a post-processing step. What we are doing, we are not putting all the circuit elements into the 3D model. We are calculating a set of voltages and currents at each of the pin of the circuit and at each of the pin of the 3D block. And each pin of the 3D block corresponds to one port. And once I know what is the voltage and current distribution at each pins, I can apply them to the ports. And by using superposition, I can calculate the field distribution. And that works as superposition, as most of you know. It works only in frequency domain because only superposition can only be applied for linear systems. So here's the example how it works. So I have taken again my microstrip, but I put a hole in there. And first I simulate again with the broadband simulation, as I always did before. So I run it. Now I have to go through 4 different ports because I have placed a slot in here and one basically a bridge where I can put a component here in order to short the circuit, the slot, or keep it open. And because we want to see how this affects, I have defined field monitors at 100 megahertz at 1 gigahertz, so we will see the surface current after it finished. So in order to use the combined results approach, the 3D, so I need to predefine the monitors, because what the 3D solver will do, basically it will calculate the surface current for each of the ports. You can see in this rectangular brackets, 1 means this is the surface current distribution when port 1 is excited. It's mostly on the trace. This is the surface current distribution when port 2 has been excited, which is of course similar to 1. This is the surface current distribution for port 3. Just wait till it finishes. I have to click one more time. Okay, and then I get a surface current distribution for port 4 when it finished. So what I get is the surface current or the electric field, whatever field I want to see, for each port separated from each other. This is not an overhead to a standard simulation, because this is the same approach that I need to choose if I want to calculate S parameters. So once I have calculated this broadband setup and I have calculated all the field monitors, and you can see of course that port 4 creates a pretty different current distribution than the other ports, of course, because it's placed here. So once I have calculated everything, I go again to the schematic, and now I have the same setup as always, with the termination, with the series and the driver, and I keep port 4 open. I don't connect anything there. Now I define a task, and instead of using a transient task, a switching task, I use a frequency domain task, AC, alternating current. I think this is also what you typically might know from SPICE simulations. And in this setup, I said that port 1 will be driven with a voltage at a magnitude of 1 volt. So that means at each frequency that is excited, a magnitude of 1 volt is chosen. And then I have a tab here, which is called combine results. And when I activate combine results, we will see what happens. After starting this task, you can see it's called post-processing combine results. It just took 2 seconds. It was very, very fast. But of course, I can again visualize the voltages at the probes on the circuit level, but that's not what I'm interested in. If after the combine results finished, you can see that into the navigation tree of the 3D model, there are some new entries, and there is an entry which is called AC1. And this is the surface current distribution, basically considering the circuit that I have attached. And of course, what was see here in this setup is that the current runs on the signal trace, and then it cannot flow through the split. It has to flow around it, and that happens at 100 megahertz, and it happens at 1 gigahertz the same way. So that's pretty what I would have expected in this case. Oh, sorry, I should click here. This is the setup where we see the current, and current flowing on the signal trace around the split, but nothing flows through port 4. So like I said, now we can connect elements and see how these elements affect the current distribution in frequency domain, but without rerunning the 3D simulation. So what I do now is I place a stitching capacitor, basically, that stitches these two metal layers to each other. I connect it at the port 4 and I give it a value of, for example, 100 pico, like 0.1 nano. And now I just take the AC task and I duplicate it to get another AC task, and combine results, everything is active. I just rerun the same thing, but now I have the cap connected. And when I go back to the 3D model, what you see is that I have both results from AC1 and from AC2. At 100 kilohertz with the cap, at 100 megahertz with the cap connected, not much is happening. The current is still flowing around here. However, if I go up to 1 gigahertz, you can now see that at 1 gigahertz, the cap that I have connected onto the schematic becomes a short. It can conduct, and you can see how the return current, instead of going only the one way around, the return current will flow also through the second cap, because I have added it to be here onto the schematic. And you could see that's very, very quick. It took just 2 seconds because it is reusing the data that has been previously calculated by the 3D solver. So this is the idea of the combined results, and this is very, very powerful because it gives you the access to the field results basically at the speed of a circuit simulation. And what I have done up to now was in frequency domain with the model that you see here. But in the CSD version 2016, we are adding a extension of this frequency domain approach. It's a combined results using transient simulation. Basically what is happening in the background is the same superposition principle that I showed you before, but what we are doing, we are getting the frequency domain data by a Fourier transform of a previously simulated transient task. So instead of defining the AC task that I did before, I can really define a transient switching task. And what will happen is that once the transient task is finished, the signals, the time domain signals are transformed into frequency domain, and they are applied in the same way we did it in the combined results in frequency domain. They are recombining or superpositioning the examples from the 3D model. And this is very powerful when you have nonlinear elements, because what it gives to you, of course, it is still superposition, so it cannot capture transient effects. It's not a transient monitor, but it is a frequency domain representation of the switching behavior of your circuit, of course always assuming that your circuit is in steady state. So that is pretty complex, but it has widespread usage, for example, again in power electronics. And what I did here, I have also created an example file. Let's go back here to the strip, and we have some parallel component that I place here. And this parallel component, now I place something nonlinear, like a diode. So what I can do now after this, so the 3D model has been already simulated at this point, and I go to the transient task and I update it to show you the effect of the diode. So the diode is of course preventing some switching, and I can see the time domain voltages. So now the excitation signal goes from minus to plus 10 volt, and you can see that at the termination side basically only the positive signal is arriving because the diode blocks the other signals. Okay, that's how a diode should work. But you can see that I have done also a combined results from this transient task. So this is a little bit short, so therefore I increase the signal time, because like I said, we need to make sure that the system is in steady state and we capture enough of the switching behavior. So I just increase the simulation time of the transient task. That's what it gives to me. I can go back to, for example, look at the surface current here in this case. Like I said, this is not the transient, it's a surface current, it's a frequency domain representation of the switching behavior. But I don't want to go too much into this. I want to show you a different applicability of this approach is by using also field probes. So for example, if you want to look at radiated emission, I have placed a field probe basically at 3 meter distance above the PCB. And this field probe, so not only the 3D results, also this field probes, they are combined by using the combined results. So what I can look at now is that the emission or the electric field at a 3-meter distance, when the system was driven and was containing the probe, how does it look like? This is what I get. This is the emission spectrum now right away in dB microvolt, when I had included the diode. And now, of course, what would be, for example, pretty interesting is how will it change when I just remove the diode. So I remove the diode here, and like I did before in the AC task, I just duplicate this particular task and rerun it in the same way. So it's rerun and combined results is applied to it. And I can really see what is the effect of this particular diode on the emission at 3-meter distance. And this is tran 1 when the diode was included, and this is tran 2 where the diode is removed. And you can see that the diode has a pretty significant effect there, of course, because the complete current path has been completely changed by adding the diode. But you could really accurately see here, also you can see that some certain frequencies that have been included in the spectrum while the diode was included, they are completely gone when the diode has been removed. This is something you would expect. But again, it's not only giving you the circuit results, it's also giving me the emission or the field values at certain distance, including these nonlinear elements. This is a new addition to the Studio Suite 2016, and I think it's really powerful if you want to run EMC simulations. So that brings me to a more practical example. I'm basically through with the theory. So what you see here is a recent project that we done at CSD. It's a very simple DC-DC converter which converts the voltage from 12 to 5 volt. We made a layout here and also produced a prototype for this, and with all the techniques that I've been showing you during this webinar, the structure has been analyzed in order to calculate the conducted emission at this point. So you can see there is really a lot of ports placed into this structure, but that doesn't matter. You can simulate this easily and do these ports. What we do is we connect our circuit elements. Of course, every system typically will start with a standalone circuit simulation, as we can see here. This is a very typical down converter, and we use just a simple switch to switch the voltage on and off. We have the switching loop here, a boost loop, and a load here. And with this standalone circuit, we first check if the system is doing what we expect to. Yes, it does. It converts from basically 12 volt down to 5 volt output. So this is just a check. And now, of course, we would like to couple this more complex circuit to this to the PCB model. And this is what we do. So here is the PCB one more time, but you can see it has been now simulated not with the time domain but with the frequency domain solver, because we have a pretty high count of ports. It's 22 different ports that has been placed there, and a pretty low frequency range, so it's ideally suited for the frequency domain solver. And you can see running this setup, it took not even 2 minutes on a standalone laptop. So this is 3D solvers, I think, came a very long way, and that they are able to simulate even complex structures at a pretty good simulation time. And what you see, for example, also here, what I wanted to add to you, that the technique of using the virtual reference, what I showed during the webinar, to be used for the transistors, can also be used for connectors. So basically the input connector which delivers the input voltage to the board is also modeled by using such a virtual reference. So this is really quick in the 3D side. And then what I do, in the same way that I have connected all the elements during this webinar, I connect all my switching elements, the diodes, the capacitors, the line impedance networks. I connect them all to this block and run out the full coupled simulation. It takes some time till I reach steady state, but for 350 microsecond simulation time till the steady state of 5 volt is reached, it takes approximately 3 minutes on my laptop. And I use combined results together with this, which allows me to visualize currents and also to obtain the emission from the setup. And what we can look at here is that this is a demonstrator we have implemented in a way that we can use jumper switches to switch on and off our input filter, and the structure has been measured with the filter on and off, and we have been simulating this just by connecting this particular pins here to just shorting these pins is like switching the filter on and off. So in the same way that it's done by jumpers, we can define such jumpers in Design Studio, and we can compare then the simulation and the measurement results. So here is the unfiltered value where we have like 95 dB microvolt of conducted emission, and this is the filtered value where the emission drops to 53, and you can see there's a very nice agreement of the simulation and measurements. And like I said, it's not only working for the emission curves, we can also visualize really the fields. And what you can see here is that when the filter is switched on, so this is basically the input branch, the electric field at this input branch is filtered. So exactly here at this position at the filtering elements, you can see that the fields drop off after passing through the filter, while in the case where the filter is switched off, you can see a pretty high voltage here at the output that will lead to emission. So it's also pretty useful to use these field monitors because, for example, you can use them to find the best position for a filtering element that you want to place onto your PCB. So it's really helpful to have also this visual representation of the current and field distribution. So let me summarize today's webinar. So I have showed you concept of coupling a 3D simulation and a circuit simulation by using S parameters on the schematic. There are a few new things that you need to learn because such a coupled simulation is somehow an extension of a standalone circuit simulation, and the ground using of the ground symbol is a little bit different from what you are used to in SPICE simulations, but I'm pretty sure that it is not too complicated to learn this. The advantage of such a coupled simulation is of course that you can visualize 3D fields that has been calculated by inside the 3D model, considering really the circuit that has been attached to it. And this is very powerful in debugging your hardware because you can really see fields, you can see currents flowing on your structure the way they actually do when the circuit has been attached. In many cases it can speed up the total simulation time, and it also allows you to include this non-linear switching elements and visualize the effect again in terms of currents and fields of your 3D structure. And in the end of the presentation I showed you a realistic example where we could see how this concept of the coupling field and circuit simulation has been applied to a DC-DC converter. So I hope that you found this presentation interesting, and I would like to thank you for your attention. Thank you very much.